Hi, welcome to Dynamite, comparing the accuracy of differing quantum mechanical models for the light absorption of conjugated pi systems within colored dyes. I'm Sebastian Kinsler. Today, we're comparing several computational methods to some experimentally determined data to find which computational method gives the most accurate results. The chemistry we're focused on is the quantization of electronic energy states. As chemists, we know that electrons are restricted to carrying set amounts of energies. When energy, in the form of light, is given to an electron, the amount of energy absorbed and used to promote the electron from the ground state to its first excited state is correlated to the wavelength of light it can absorb by the equation E equals hc over lambda, a relationship first proposed by Planck and Einstein in 1900. Because the electron can only be promoted to levels of specific energies, and h and c are fundamental constants, the wavelength of light absorbed directly gives the energy difference between the electron's ground and first excited states, and we barely even need to do any math. In this experiment, we use UV-vis spectroscopy to determine the energy levels of 4 differently colored dyes. Then, we use 3 different methods of calculating the theoretical energy levels based on molecular models and theories. The models used, which we'll talk more about later, were particle in a box, Huckel molecular orbital theory, and Cygress, a software using models based on the Hartree-Fock and NDDO neglect of diatomic differential overlap models. 2 hypotheses were made before performing the experiment. Remember these because we'll address them in just a few minutes. First, we thought the dyes with longer aromatic systems would absorb UV-vis light at higher wavelengths due to the increased length of the pi system stabilizing the active region of the molecule. Next, we predicted that the Huckel model would be a more accurate predictor of theoretical absorption wavelengths than particle in a box. This is because the Huckel model accounts for more quantum mechanical phenomena like orbital overlap. So the first thing to do was to find the energy levels of each dye and get experimental data. The setup looked like this. A beam of light exits the light source, is focused by a lens, and redirected by a mirror into our sample of liquid dye. Then it hits another mirror and another lens and enters the detector. The light source is composed of a typical white incandescent bulb and an ultraviolet LED to fill in the short wavelengths that the incandescent bulb doesn't reach. The 4 dyes used were super simple in chemical composition, but differed in the length of the carbon pi system separating the 2 cyanine moieties. The shortest dye, 3,3-diethyl thiocyanine iodide, has only 1 carbon connecting the 2 rings, while the longest dye, 3,3-diethyl thiotricarbocyanine iodide, has 7 pi conjugated carbons in the space. Changing the length of this chain changes the electronic environment experienced by the electron, altering the energy difference between its ground and first excited state, and therefore changing the wavelength of light the dye absorbs. Here, we can see the UV-vis spectrum recorded by spectroscopy into the software Logger Pro. Once this data is obtained, finding the energy difference is as simple as relating the peak of each of these curves to its corresponding energy via the Planck-Einstein relation. For example, the dye labeled in blue absorbs at a max wavelength of 557.5 nanometers, which equals a delta E of 2.23 electron volts. In this table, we see that the wavelength of maximum absorption gets larger as the corresponding energy difference becomes smaller. Next, let's talk about particle in a box. The particle in a box model estimates the energy of an electron in a pi system to be the direct product of the length of conjugation, the size of the box. This equation, E equals n squared h squared over 8 ml squared, gives the energy of a given particle in a box. For our dye molecules, the length, L, is found by counting the carbons separating these 2 cyanine moieties. After performing all these calculations, the energy difference of each dye was found to be 6.17, 4.54, 3.60, and 2.97 electron volts. Again, we observe the trend of energy decreasing as the size of the pi system increases. Next, let's talk about Huckel molecular orbital theory. This model is much more in depth than the particle in a box model, as it attempts to solve the Hamiltonian of the molecular wave function by linearly combining atomic orbitals. To do this, a matrix is created by combining each adjacent molecular orbital, accounting for the energy of the electrons in the independent atomic orbitals and the energy received from overlapping. Thankfully, we have computers that can set these up and solve these matrices for us. And this experiment, Mathematica and MathCAD, were used to create and solve matrices for each of the 4 dye molecules, calculating delta E results of 1.4, 1.071, 0.868, and 0.728 electron volts. Lastly, the most complicated computational method utilized in this experiment was Cygress. This software allows users to create molecules from scratch and then analyze their behavior using a myriad of algorithms. Here, we have a model of 3,3-diethyl thiocyanine iodide made in Cygress. Nitrogens are blue and sulfurs are yellow. After creating our molecules, we compared 4 different algorithms Cygress is capable of solving: MOS, MNDO, AM1, RM1, and PM3. These 4 methods all use the MOS molecular orbital package, which is especially good at considering a molecule's spectroscopic properties. Using Cygress, we generate data tables of the molecule's predicted absorption across a range of wavelengths. Then, we process this data exactly the way we processed our experimental data using the Planck-Einstein relation. To make all these abstract numbers easier to interpret, let's make a table compiling the results from each computational method and the experimental data. Then, we calculate and use percent errors to assess the accuracy of each model as compared to the experimental results, which we're assuming to be perfectly correct. Now, let's address the 2 hypotheses we made earlier in the video. First, we predicted that the dyes with longer pi systems would absorb light at higher wavelengths. This was definitely reflected by every method used in the experiment. Remember, high wavelengths of light correspond to smaller differences between the energy level of the ground state and the first excited state. Because the larger pi systems stabilize the electrons within them, the dyes with longer chains were always predicted and recorded experimentally to absorb light at the lower energy high wavelengths. Next, we thought that the Huckel model would better match the actual energy differences of the experimental results than the particle-in-a-box method. We said this because the Huckel model accounts for some quantum mechanical phenomena that particle-in-a-box does not. This hypothesis was found to be true when analyzing the percent errors. The Huckel model was about 60% closer to the experimental values than particle-in-a-box. However, Huckel is still too simplistic to be the most accurate predictor tested in this experiment. Its accuracy is affected by its reliance on approximations and simplifications, and it omits several crucial factors, like the famously difficult electron-electron repulsion, or how parts of the molecule outside the pi system affect the electrons within the system. For example, the size of the box utilized in particle-in-a-box calculations is subject to the identity of the atomic end groups. For these dye molecules, it was necessary to include extra bond length beyond the carbon chain due to the extra conjugation provided by the doubly bonded nitrogen end group. However, additional complication is introduced when the end groups of a conjugated carbon chain change in polarity. The size of the box can be affected by this change in charge, as the electrostatic interactions between the positively charged end group and the negative electrons within the box interact. The electrons become localized towards the positive end of the box, therefore changing its length in a way not accounted for in our calculations. However, the computational software Cygress is able to account for small discrepancies like this, which is why Cygress was a consistently better predictor of the energy difference than both the Huckel model and particle-in-a-box. The largest percent difference from a Cygress method was 18.7 from both the MNDO and RN1 algorithms, which is 33.5% smaller than the Huckel model and 92.1% smaller than particle-in-a-box. The best Cygress theoretical model was AM1, which produced a percent difference of just 16%, making it the most accurate predictor tested in this experiment. When analyzing the models behind each Cygress theory, we can see why AM1 is the best of the four models, as they're all intimately related. AM1 is just an improvement of the MNDO model with less repulsion between close atomic cores and twice the number of parameters per atom as MNDO. Additionally, PM3, the second best Sigris model, differs in the fact that it treats some parameters as variables, while AM1 takes advantage of actual spectroscopic measurements, making it perfectly suited to the nature of this experiment. Interestingly, RM1 is a reparameterization of AM1 introduced 20 years later and is reported to have much lower margins of error as compared to AM1, PM3, and their common predecessor MNDO. So we may expect it to be the most accurate predictor of the group. However, again, RM1 optimizes parameters instead of using spectroscopic measurements like the most accurate model, AM1. So it's possible that while RM1 may be more accurate for predicting things like bond lengths or vaporization enthalpies, AM1 was best suited to the spectroscopic nature of this experiment. In conclusion, we found many methods that can predict the energy difference between the ground and first excited state of an electron delocalized within a pi system, and therefore the wavelength of light the electron absorbs. If you have access, Sigras was by far the best method tested in this experiment, and the best of the four tested MOS derivative models in Sigras was AM1, but only by a marginal improvement. An additional reason why Sigras may be the preferred method over Huckel or particle in a box is because Sigras eliminates the possibility of calculation errors that come from doing math by hand. However, a drawback may arise when analyzing very complex particles, which may be difficult and time-consuming to construct within the software as compared to the simple addition of bond lengths needed to perform particle-in-a-box calculations. But for relatively simple molecules, like the four dyes used in this experiment, it was easy to build and analyze them within the software. Overall, we found Sigras to be the most accurate, efficient, and effective method for performing quantum mechanical analysis on conjugated pi systems of electrons. Thank you.